Okay, so today we wanted to go back to some of the basics of calibration and go away from some of the more intricate sales details and sales processes, focus more on what we're doing when we perform a calibration. In specific, we're going to talk about the exciter and the effect it has on calibration results and why it's important. So first, why do we care about the concept of uncertainty? This is something that when you are using a calibration system or considering to purchase a calibration system, this topic comes up quite a bit. And the reason we care is that when a customer sends their sensor for calibration, they essentially want to know if the sensor is good or if it is bad. And how good your uncertainty is your ability to answer this question to the customer. And if you do it incorrectly, lots of people are unhappy. The customer is unhappy because they have a sensor that they believe is broken. And they call up Mr. J. They say, Mr. J, I've got this sensor from you, and I've used it for a year, and I've calibrated, and now it's not working. Mr. J looks at the sensor, and now Mr. J is unhappy because he has a sensor that the customer is unhappy with, so he sends it to PCB. PCB is unhappy because they're getting return inventory, and then PCB tests it and says, there's nothing wrong with this sensor. But in the process, everyone is now unhappy because a sensor is damaged. So having control of a calibration lab's uncertainty will improve our ability to correctly determine if a sensor is good or bad and avoid the situation where customer, distributor, and the factory are all unhappy. So why is the exciter so important in this determination? Well, it's the centerpiece of the calibration system. It is providing the mechanical excitation to both the reference and the test sensor that is used to make the measurement of the sensor and determine whether it's good or bad. We assume, in an ideal sense, we want the shaker to move in one direction, not in a side-to-side direction, and we want the two sensors to remain rigidly mounted to each other. Also important considerations for the shaker, it is the mechanical piece, so we want it to be easy to use. And we also want it to be durable because it's going to see lots of cycles. So I'm going to divert from the presentation shortly. I'm going to go to camera. And what I have set up here is a PCB teardrop accelerometer on a flexure calibration exciter. And I chose the teardrop because it allows me to mount it in whatever direction I want. The mounting of the sensor is good. So what I'm going to do now is run a calibration of this sensor. Frequency sweep. I'm focusing mainly on the high frequency area. I'll tell the system to run. So envision this being a calibration lab who is testing a sensor. They receive the sensor, they mount it on the shaker, and they start running the test. They're collecting data, and they look at the initial value. Okay, it's 11.23 millivolts per G. That's good. Frequency response at the high end looks good. Continue collecting our data. Then all of a sudden, oops, the sensor must be bad. It does not pass frequency response. Again, and we'll go back to the presentation, and we will explore why this sensor does not pass. And it goes to this concept of transverse sensitivity. when we design an accelerometer, we want it to measure motion in one direction only. But because of our manufacturing limitations that every manufacturer has, all sensors pick up, are sensitive to motion in the off axis. In other words, when we shake the sensor side to side, we get output. This is normally expressed as a percentage of sensitivity. So when you see a 5% specification, transverse specification, that means that when we shake this in the transverse direction, we get 5% of its axial sensitivity in output. We now look at the exciter. For this particular exciter, the transverse performance is that of the blue line. So when we get to certain frequencies, we get very large side-to-side motion. Now, if we plot this on a polar plot, this is what's happening. At the transverse resonance of the exciter, we're getting very large motion in the direction of the red arrow. The transverse sensitivity of the reference sensor is of the blue line. So when we get this transverse motion, the reference sensor does not respond to the motion at all. However, the test sensor, the transverse sensitive axis of the test sensor, is perfectly aligned with the direction of transverse motion. So the transverse motion creates output on one sensor, but not the other. This causes a difference in results and causes the sensor to fail. Now, what I'll demonstrate here next is how realigning the transverse sensitive axes of these sensors will cause the sensor to pass. In other words, it will look more like this plot, where the direction of transverse motion is not in the direction of transverse sensitivity of the sensor. So if you bear with me for a moment, I will come over here and move my sensor. Of course, we need the surfaces to be clean. Now, if you were paying attention and you saw the original orientation, the sensor was oriented, I'm trying to move my hand out of the way, like this. What I'm going to do is I'm now going to change it so it's oriented like this. A little glue on it. Okay, unlock the shaker. We'll go back to the software. We'll rerun this calibration. Now, while this is running, the important thing to know is that when we receive a sensor from a customer to calibrate, we don't know which direction the transverse sensitive axis is. We also don't know the direction of the transverse motion of the shaker. So of course, to do this demonstration, I had to do some investigation ahead of time to find out where the right directions were. Most labs would not know that. Oops, I didn't get it quite right. Let's see how the rest of the test runs. Okay, and I need to apologize. I think I put it back in the exact same orientation that I had it in. Okay, let's try one more time. My apologies. Roughly 45-degree rotation is what we're targeting. Okay. Okay, now I believe I have it in the correct orientation. So, let's try one more time. So again, we're running the calibration. And again, the sensitivity at 100 Hertz is about the same as what it was. And this one is looking more like it was supposed to. Yes. Okay, so that was where the sensor failed last time, and as we can see this time, it's passing no problem. I'll let that complete the rest of the way. So what we've done is successfully realigned the axes, the transverse sensitive axes of the sensor with the reference, and gotten the transverse motion of the shaker to not play a role. Now, for users, this can be a particular challenge because to deal with the issue of transverse motion, the user will either need to skip the frequencies that are problems, which sometimes is not practical, and sometimes they are at different points, or they have to remount the sensor multiple times to get the sensors lined up correctly. The third option, which is the option that we recommend, and something that we've been focusing on quite a bit over the past couple of years, is to just eliminate the transverse motion. So if I go to some test data that we've collected in the past that we obviously can't collect today, if we were to repeat this test over and over again, rotating the sensor in 30-degree increments, these are the variance and results that we'll get. And notice that sometimes we get stuff to pass in one area, but then fail in the other because the transverse motion is in different directions and depends by frequency. So really the best way to eliminate the problem of transverse motion of the exciter and the effect it plays on transverse sensitivity is to just go to a shaker that does not have transverse motion, which is the advantage of the air-bearing shaker. Here's the data that we collected. Same test, same sensor on the air-bearing shaker. You can see very consistent at all frequencies. And it should also be noted that when we have problems with transverse sensitivity, there's nothing wrong with the sensor. All sensors have transverse sensitivity, and even sensors that are well within spec can fail because you excite them